Hello everyone, I'm Yao Chen from Shandong Institute of Advanced Technology. Today I'm going to present you the new properties of secondary cosmic rays observed by the alpha magnetic spectrometer on the International Space Station on behalf of the AMS collaboration. Primary cosmic rays, including proton, helium, carbon, oxygen, as well as the heavier one, near magnesium, silicon, and iron, are produced during the lifetime of stars. They are accelerated in supernova explosions and then injected into the interstellar medium, propagating through our galaxy. Secondary cosmic rays, lithium, beryllium, boron, as well as the heavier one, fluorine, are produced by the collision of primary cosmic rays and interstellar medium. AMS found that there is the third group of cosmic rays, which are linear combinations of primary and secondary cosmic rays. So they have both primary and secondary components, including nitrogen, sodium, and aluminum. AMS has already performed the precise flux measurement for light cosmic ray nuclei, including primary cosmic rays, helium, carbon, oxygen, as well as the secondary cosmic rays, lithium, beryllium, and boron. We also performed the flux measurement for nitrogen, which is a combination of both primary and secondary components. We found that the primary cosmic rays, helium, carbon, oxygen, have identical rigidity dependence above 60 GeV. They all deviate from a single power law and hardening in an identical way. Similarly, the secondary cosmic rays, lithium, beryllium, and boron, they have identical rigidity dependence above 30 GeV, and at high rigidity, they deviate from a single power law and hardening in an identical way. However, we found that the secondary cosmic rays harden more than the primary cosmic rays, as we can see from the plots. Recently, AMS also performed the precise flux measurement for heavy primary cosmic ray nuclei, the neon, magnesium, and the silicon one. We found that above 86.5 GeV, the neon, magnesium, silicon flux have identical rigidity dependence. At high rigidity, they deviate from a single power law and hardening in an identical way. However, the rigidity dependence of neon, magnesium, and silicon are different compared to the helium, carbon, and oxygen one. So there are at least two classes of primary cosmic rays. The lighter one, helium, carbon, oxygen, and the heavier one, neon, magnesium, and silicon. And here comes the question naturally, how is the rigidity dependence and flux shape for heavier secondary cosmic rays, fluorine, sodium, and aluminum? So in this talk, I will cover the measurement of sodium, of fluorine, sodium, and aluminum flux measured by AMS, and for the measurement of primary cosmic rays, as well as the isotopy for lithium, beryllium, together with the deuteron. These topics will be covered by these talks given by my colleagues. AMS measures the rigidity of incoming particles using 9 layers of silicon checker and the permanent magnet. The coordinates or the heat position for the incoming particles will be measured by the silicon checker, and from the heat position, we are able to reconstruct the particle trajectory. By using the curvature of particle trajectory inside the magnetic field, AMS is able to perform the measurement of rigidity. And the coordinate resolution for silicon checker for the fluorine up to silicon is around 6 to 8 micrometer, and it leads to a maximum detectable rigidity of 3 to 3.5 dB. Incoming particles are also required to have consistent charge measurement along the trajectory, measured by checker layer 1, the upper time of flight scintillator counters, the upper TOF, the inner checker, which is 7 layers of silicon checker from layer 2 to layer 8, as well as the charge measurement by lower TOF and checker layer 9. The combined charge inner checker, the combined checker layer 2 to layer 8 charge measurement has the charge resolution of around 0.13 to 0.17 charge unit for fluorine and up to silicon. And here it shows the inner checker charge distribution for fluorine, sodium, and aluminum together with the nearby charges. Thanks to the good charge resolution, as well as the redundant charge measurements by different sub-detectors, AMS is able to clean the fluorine, sodium, and aluminum event samples despite their much lower abundance compared to the nearby primary cosmic rays. The fluorine nuclei were selected using charge measurements on the inner checker and the upper TOF. The residual background below checker layer 1 can be precisely subtracted by the layer 1 measured charge. The so-called below checker layer 1 background is resulting from heavier nuclei such as neon interacting with the materials of TRD and upper TOF. So after the very precise, accurate treatment of the systematic uncertainties, AMS finally obtained the fluorine flux as function of rigidity. In order to compare with other experiments, we converted our measurement into a function of kinetic energy. So this plot shows the AMS measured fluorine flux as function of kinetic energy from 0.5 GeV per nucleon up to 1 TeV per nucleon, and compared with other experiments. It shows that the precise measurement of the fluorine flux is able to reveal the detailed flux shape. To better understand the fluorine flux rigidity dependence, we compared our measurement together with the lighter secondary, the boron flux. This plot shows the AMS fluorine and boron flux measurement as function of rigidity from the 2.15 GV up to 3 TeV. And it shows that both the fluorine and the boron flux are deviate from single power law at high rigidity and hardened there, and also they have identical rigidity dependence at high rigidity. We also want to compare the heavier secondary to primary flux ratio, namely the fluorine to silicon ratio, to the lighter one, the boron to oxygen one. The fluorine to silicon flux ratio, we found that can be fitted by a double power law above 30 GeV, and fluorine is hardening more than the primary silicon flux. We also found that surprisingly, the fluorine to silicon ratio have different rigidity dependence compared to the lighter one, the boron to oxygen flux ratio, which can also be fitted by a double power law at high rigidity. However, the fluorine to silicon flux ratio divided by the boron to oxygen flux ratio can be fitted by a single power law above 10 GeV. So it reveals that the propagation properties for heavy cosmic rays from the fluorine to silicon is different compared to the propagation properties of lighter cosmic rays from helium to oxygen. We also performed the precise flux measurement for sodium and aluminum. And the left plot shows the AMS measurements converted into kinetic energy from 0.5 GeV per nucleon up to 1 TeV per nucleon for sodium and aluminum flux, together with other experiments and simulations. It again shows that the precise flux measurement is able to reveal the detailed flux shape and the dependence for sodium and aluminum. The right-hand side shows the AMS measurement of sodium and the aluminum flux as function of rigidity, together with the flux of nitrogen. And we found that at the low rigidity, the sodium and the nitrogen have the identical rigidity dependence, while for aluminum and the nitrogen, at the high rigidity, they have identical rigidity dependence. Similar to the nitrogen, we found that the heavier cosmic ray, sodium and aluminum, can be described as a linear combination of primary and secondary flux. For the primary flux, we are taking the flux shape of silicon, and for the secondary flux, we are using the flux shape of fluorine. And it shows that the sodium and aluminum both have primary and secondary components, similar to the nitrogen flux. And up to now, AMS has performed the precise flux measurement from helium up to silicon. And we found that there are two classes of primary cosmic rays, the neon, magnesium, and silicon, the heavier one, and also the lighter one, helium, carbon, and oxygen. There are also two classes of secondary cosmic rays, the lithium, beryllium, and the boron, and another class, the fluorine one. And besides the primary and the secondary cosmic rays, there is the third group of cosmic rays, namely the nitrogen, sodium, and aluminum. They have both primary and secondary components and can be described or fitted by a linear combination of primary and secondary cosmic rays. And finally, it comes to my summary. The precision measurement of the heavy cosmic ray fluorine, sodium, and aluminum nuclide spectrum from 2.15 GeV to 3 TeV based on events collected by AMS during the first 8.5 years of operation have been presented. The heavier secondary to primary fluorine to silicon flux ratio rigidity dependence is distinctly different from the lighter boron to oxygen or boron to carbon rigidity dependence. In particular, above 10 GeV, the fluorine to silicon ratio to the boron to oxygen ratio can be described by a single power law, revealing that the propagation properties of heavy cosmic rays from fluorine to silicon are different from those of light cosmic rays from helium to oxygen. Sodium, aluminum, and as well as together with nitrogen belong to a distinct cosmic ray group and are the combinations of primary and secondary cosmic rays. AMS performed the model-independent measurements of nitrogen to oxygen ratio as 0.092, the sodium to silicon ratio as 0.036, and finally the aluminum to silicon ratio as 0.103, abundance ratio at source. And thank you so much for your attention.